Welcome everyone. Sorry for holding you up. Hopefully you don't have to be there somewhere else too soon. We invited Stefan. He's external tomorrow. So just a few words to introduce you, if that's okay.
Okay.
Yeah. Won't do the bio exactly as it is. So Stefan studied physics at Harvard. Spent some time doing a project at IRCAM. Harris after that, before completing an MSc and PhD at Stanford. Then after a postdoc at Space Telecommunications and Radio Science Laboratory at Stanford. Don't know what you did there, Stefan, you can tell us another later.
Ground penetrating radar.
Oh.
Actually, it was too short to get into it though, really.
Yeah. He began life as an academic actually here at Queen's, based at SARC. He was here during the opening of the building and indeed of the Institute when Karl-Heinz Stockhausen opened the building in 2004. So it's great to have you back, Stefan. In 2005 you moved to University of Edinburgh and became professor of audio and acoustics there in 2016?
Maybe,
yeah. Yeah, somewhere around there. His main research focuses on physics-based audio, as reflected in the talk today. So during his time in Belfast he published a book on wave and scattering methods, and at the end of that book he proposes that the network apparatus involved in such methods is a bit cumbersome, and that maybe we should, if we want to look at things in acoustics, we should be relying more on general methods such as finite differences. He then wrote a book on finite differences in musical acoustics and hasn't really looked back, I suppose. Applying this to a huge range of sounding systems, rooms, musical instruments, and so on. And when I say applying, actually Stefan left quite a trail of novel ways of constructing finite difference schemes, much along the line of Hamiltonian methods, so they can handle peculiar nonlinearities and domain irregularities and so on arising in musical instruments and room acoustics. He's also invested quite heavily linking this work to multi-channel audio, large-scale audio rendering using GPUs, and working with composers in electroacoustic music. So today's going to give us an overview and updating us on the latest development in this area.
Okay, cool.
Thank you, Stefan.
Yeah, thanks a lot.
So let's give him a short welcome.
Okay. Yeah, thanks a lot, Martin, for the introduction. It was really, really interesting to be back. Like, I left 20 years ago. So it's amazing how much you guys have filled the building, actually. It's incredible. We were just 2 floors when I was here, I think. All right, so this is kind of more of a, actually slightly more of a music talk, actually, than engineering talk. So it's kind of geared towards, composers. But there is some technical stuff, like, towards the latter part of it, but nothing, like, too heavy. So what I'll do is I'll just kind of give you an overview, take you through kind of a sort of a gallery of some of the things you can do. Talk about the computing aspects, and then talk about the music as well. Okay, so just a word about our group. So we're like a kind of a very small version of SARC, I guess. I don't know what you'd call it. I mean, at least 2 people in this room have connections to it, right? Called the Acoustics and Audio Group. And so we came out of the School of Physics, and then eventually ended up in the School of Music. So our areas are mostly experimental computational acoustics, audio signal processing, music tech, and there's like 5 of us who are kind of on the tech side now. So we've expanded and just hired a couple more people. So Tom McKenzie and Alec Wright are doing spatial audio and audio machine learning. And then we work pretty closely with the sound designers and the recording people. So Martin Parker, Jules, and Roderick. And we run a few sort of degree programs too. So that's kind of like most of the business of what we do there is running these 3 programs. Okay, so I'll skip ahead here. So just in terms of an overview, physics-based audio, I think just because Martin's here in the building, you probably know what this is. But the idea is just to try to obtain high quality, natural sounding acoustic sound purely through simulation. And there are really 2 main branches of this kind of work. So there's the synthesis side of things, where you go and do a physical model of some instrument which exists out there in the real world. Or you can go and sort of develop, physics-based models of things that don't exist out there, like this weird sort of vibrating set of 5 bars, which forms the basis for a plugin that we sell now through our company. So that's the synthesis side here. So here is just audio out. And then there's effects processing, where you have some audio in going into some system represented physically, which then transforms that sound. And there are two main examples of this would be the big problem of room acoustics, and then also something like a spring reverb. And I put this in for the sake of Jacob, who's doing his Viva tomorrow on exactly this topic. And there's also, of course, virtual analog electronics, so people who do models of things like amplifiers and pedals and stuff like that. That I won't talk about today, but that's actually a really big part of what you might call physics-based modeling. Okay, now just like a word about audio versus data-centered approaches, physics-based audio versus data-centered approaches. So the big distinguishing feature is that it's algorithmic. So we're not using any samples here at all. And this has some implications. So one is that the codes themselves are really small, right? So if you have a typical physical modeling code is on the order of kilobytes, right? So you're not sending over big tranches of data when you're sending over an instrument, so they're tiny. But the compute and memory costs, like when you actually run these codes, are highly dependent on what you're trying to model. So if it's some reasonably sized instrument, so something like a wind instrument, it can be very small. For something like a room, it can be just enormous. The parameter sets are also quite small. So these are usually like physical dimensions or descriptions of the materials that make up an object. So you normally just have a handful of these when you're describing an instrument. Sometimes they're hard to get though. That's one thing I think like people who work in physical modeling know, is that you can find these numbers in books, but then sometimes, like, I don't know, if you have something weird like a wound string or something like that, like how do you go and figure out what the density is of the cross-sectional area and stuff like that. And people go and extend these to include samples for parts of these model things that are hard to model. So something like a key click, for example, is a good example. So something you wouldn't want to invest a lot of compute trying to model, and that's actually relatively static. So something like a key click, you would just go and sample that, and you could add it in. So it depends, how pure you want to be about this. But these algorithms always operate as recursions at an audio sample rate. So these are sort of feedback IR systems, sometimes like highly nonlinear. And that's kind of the best way to think about them, really. They're distantly related to something called procedural audio, which people probably know something about, which is also an algorithmic approach to generating sound. But it's slightly different. Like here, in physical modeling, we're talking about the equation that describes something as being the kind of ground truth. Whereas, like sometimes, like in procedural audio, you're looking at special solutions and using those as the way to generate your output. And probably most importantly, there's no training in these. These are pure deterministic algorithms. The model itself is the ground truth, not the audio that it generates, which is really different from what people do in machine learning, where the audio is what you're training against, so that's the ground truth. But there are lots of points of contact between machine learning and physics-based modeling. That's what my current PhD students work on, is trying to look at these connections. Okay, so today I'm just going to go over the strict stuff, like the classic kind of physics-based modeling. So the classic approaches go back to as far as 1962, so the very first attempt at speech synthesis actually was a physical model, so a concatenated set of acoustic tubes. The first kind of musical instrument model came in 1970. So this was a master's student at Urbana-Champaign in Illinois who came up with the very first kind of mainstream finite difference method for a string. And then there were kind of weird varieties that appeared, like in the 70s there were mass spring networks that showed up in 1979. Then there was modal synthesis, which became a software package known now as Modalis, sold by IRCOM. And then finally there were waveguide methods. And these waveguides are the ones that really kind of convinced people actually that it was possible to do interesting stuff in real time. So in the 1980s and 90s. So these methods are kind of old now, and at the time that they were developed, the computational power was quite limited. So there are a lot of simplifications inherent here. So for example, in the case of something like a waveguide, I mean, they work really well for, say, a string vibrating under low amplitude conditions. That's great. Or for like a cylindrical or conical tube, they work well. But for more complicated things, you don't really gain much actually, or it's very hard to extend these and to retain that efficiency advantage. So what happened was that in the 90s, there were some pure musical acoustics investigations of more complex instruments. And the first one that I know of dealing with a much more sort of complicated system was the modeling of the timpani drum, going back to Rauti, Shen, and Jolie. And they did a full 3D model of a drum, including all the different components. So the shell, membrane, the acoustic field inside and outside. I don't think they were interested in synthesis at all. So this was just to understand like how the drum works. But this was sort of where sort of modern approaches, I think, really come from actually, these kind of pure musical acoustics investigations. And they were using not these things like modal synthesis or digital waveguides, but they just went back and used mainstream finite difference, finite volume methods, things that you would use in other areas if you're working in mechanical engineering or something, or working in fluid mechanics. Like this is what you would do. And this obviously is a very large computation, so all this work was offline at the time. So let's just take a look at some of the systems that you might look at. The classic systems that people look at for physical modeling synthesis involve an excitation and resonator interaction. So there's something acting as an exciting element, which typically is small, right? Like you model it as being kind of zero dimensional. So it's either like like a hammer hitting a string or a bow touching a string or something like that. And these go back to sort of the early 80s, these kind of models, and they're still used today. Then there are coupled systems. So you might, say, try to build some kind of complicated construction out of multiple modules and allow them to interact with each other. And going further, there are systems that are heterogeneous, where you need to start thinking about multiphysics, where you have systems or parts of components of different type within a single system. And a great example is this drum, where you have a membrane supporting wave propagation, but then also the acoustic field, and then a mallet, and then finally there are just systems that are inherently complicated. And the two toughest ones I know of are the vibration of a plate or shell at high amplitudes. That's a hard one. And the other one is actually the one that Jacob is working on. So the spring reverb is the toughest linear system I've ever seen, actually. So, okay, so let me just go through some examples now with some sounds. So I'll start with wind instruments. So the typical components that make up a wind instrument are, first of all, the main bore. So we've got one main tube. Sometimes we may have bypass tubes. So if we're working with a valved instrument, we may be able to divert some of the airflow into a secondary tube. Or we may have tone holes if we're working with a woodwind instrument. There's an excitation mechanism, and then there's also a radiation mechanism too. And these days, because these models are one-dimensional, they're pretty much easily real-time. Actually, you can do all this stuff, even in something like MATLAB, it's real-time. So I'll just play a few sort of typical sounds here. So here's okay, so that's like a typical first sound you get out of a physical model. They usually sound like bad, right? Because you are learning how to play this thing. Like you were learning what kind of control signals go in. And so before you figured out how to make it sound nice, you have to make it sound bad, right? So which is the way you learn how to play an instrument. And so you can, so that is really just someone blowing into a trumpet model. So not really doing anything with their lips, just blowing in like a constant pressure. And then what you can do is learn how to manipulate parameters such as like the stiffness of your lips, like in order to play up a harmonic series. And then eventually you can sort of go and learn how to play reasonable gestures. So these are, I mean, sound examples by me, so I'm not a musician. So really, at this point, like my job is kind of over, and the best thing to do is to give this off to a professional, like an actual musician. So I gave this to Tom Mudd, one of the composers in our group, and he went and did actually a whole album. It was really interesting, called Brass Cultures. Okay, so guitars are really quite a complicated construction when you think about it. There are a lot of interacting components here. So first of all, we have the strings, but the strings themselves are all like in partial contact with this fretboard and also these bumps that are protruding from it, these frets. And then on top of that, you've got your fingers interacting with it. So either strumming the strings or pressing against them. And so there's really kind of a lot to think about, like both like in terms of constructing this thing, but also playing it, you know, like, so I'll just play some examples here. This, by the way, is also real time. Like as of about last year, actually, we finally managed to get a full 6-string guitar up and running in real time. So here's just a sort of a basic set of strings, no interaction with the fretboard or anything like that. And then you can start to do things like strum, right? So this is under I think under a bar chord sort of configuration. Yeah, so like with a sliding bar chord. So what's happening is there's a whole kind of hand coming in contact with the strings. You decide how hard you want to press, you know? Like that's a control parameter you need to supply, and then you're moving that like over time as you strum with the other hand. And then, so what you can do then is start doing kind of extended technique, right? So, so here's an example of like what happens if you do the strumming, but then your hand kind of loses contact with the strings at certain moments. So you start to be able to sort of play on the harmonics, you get this kind of additional damping occurring. And then again, like the thing to do is to go and give this to somebody like who knows what they're doing, right? Okay, so this one went off to Gadi Sassoon, who's an Italian composer, and he did an album as well called Multiverse. So that may not sound much like a guitar, but it's because he built this thing himself. So he took all sorts of liberties with the parameters that you would use to normally define a guitar and just build something of his own, you know, like just to tune to taste, really. Okay, so let me just switch gears now and talk a bit about rooms. The room modeling, so this is a very different problem. So this is a linear problem generally. And the way people have done room modeling up until very recently has been to make use of something called ray tracing, which is exactly the same idea as what you find in computer graphics. So you imagine a source somewhere in a room, and the means of sound production is that it's emanating rays, or you can think about them as particles or something, that move outwards from the source, bounce off all the walls, and then eventually are collected at some receiver, which could be a microphone, it could be your ear. And that is the model that is used for all of the sort of standard packages, so things like Odeon, CAT, Ease, stuff like that. And the problem is it neglects these important effects of diffraction. So in a real room, you have the bending of waves around corners. And this is kind of important because like it depends on what wavelength range you're interested in. So basically the problem is for audio, the wavelengths can be very long, right, compared to any of the objects that it might be interacting with, meaning that these effects are strong. So the only way to really get a proper model of sound production in a room is to go and really model all of these effects. And you can do this actually. Like it's expensive, but you can do this at audio rate. So these are some early experiments. These are for about 10 years old now. With the, I think this is the Wiener Klangstiel. Is that right? No, Wiener.
Verein.
I don't know actually. Musikverein or something?
Yes.
Is that right?
The famous concert hall in Vienna.
Yeah, right. Whatever that is. Well, you can look at this and tell me if that's correct. Actually, I'm not sure. I've forgotten.
Yeah, that's about right. Yeah.
Okay, so yeah, it's kind of, it's shoeboxy, but then like you can go and model all the seats and stuff too. So this is a dry. So that's the dry audio, and then going in to that's 10 years ago, and that was a big calculation at the time. So it was sort of roughly, you know, I think it was about 12 hours per second of output. So it was a kind of a long, it's kind of a more than a weekend job actually to get the impulse responses out of this thing. Much better now, by the way, actually. You can do this in a much more reasonable amount of time. And then you can start doing more complicated stuff actually. So the last few years, like I've been looking at, you know, sources, receivers, and also having like what happens when you start embedding objects in the field and how do you represent those. So the reason that this is so expensive, by the way, is that you can hear like all wavelengths down to about this, so about on the order of about a centimeter or two. So like you need that kind of resolution if you want to be able to represent everything that's audible within a space. So you just kind of have a fine grid, sort of about Lego sized, you know? So if you imagine filling a giant room full of Lego, like that's kind of the number of grid points, and each piece of Lego is going to correspond to some floating point number, like you need to hold in memory. And it turns out to be a lot, right? So, so for a cubic meter, you're looking at about 1 million. So that's why that's the sort of core reason why this stuff is expensive. But you can still do it, actually. Like it's GPU only, it's offline, it will be for the foreseeable future, but it's becoming sort of more reasonable, like year on year. And then, sort of circling back to music now, now that you've looked at what happens in a room, what you can then do is embed instruments within these. So you could take something like a piece of metal, like a flat piece of metal, a plate, sort of vibrating at high amplitudes, and then have it interact with the acoustic field. And the cool thing here from an artistic point of view is you can go and grab outputs wherever you want, right? So you have access to the entire acoustic field around these things. And you can go listen to it, probe it, you could spatialize it however you want. That was the thing I was most interested in by these kind of instruments. So this is stereo, unfortunately, but here's a set of gongs. And then similarly, you can do the same kind of stuff for something like timpani. So here's a set of timpani drums, you know, all within the same space. And the interesting thing here is you hit one of these things and like it sends out waves into the acoustic field and it actually sets the other ones in motion. So they're not actually independent, you know. So here's just an example of some timpani. And then finally, just on multiphysics, I just wanted to give you an example of sort of trying to build up a sound, like piece by piece, actually, so you can hear the effects of all the different assumptions that you make. So if you were going to build a model of a drum, if you were to start just with the membrane on its own, you would get a sound that is kind of like this. Right? So this is like there's no real sense of or no model any of the acoustic field around this at all. So this could be like a membrane in like outer space or something with like contact mics on it, right? You know, and that's the kind of sound it would produce, like at least on the electronic signal you get out of it. So if you then go and introduce snares to it, so snares, like if you turn over a snare drum, you know what's there, right? It's a bunch of wires that are very loosely affixed against one of the membranes. And this changes the sound like a lot. So if you, what happens is the snare will set these into motion, and then they will come back and then bounce against the membrane, but in a very random sort of way, leading to noisy timbres. And this changes the sound a lot, actually. And so what you could then do is go and put this in 3D, right? So now, in a full model of a snare drum, we have two of these membranes. We hit the top one, and then waves propagate through the interior, hit the bottom one, set the bottom membrane into motion. That sets the snares into motion. And then, on top of the sound we just had, we now have the sort of cavity modes, right? So you have this kind of ringing effect that you get in real snare drums, and you'll hear that, I think, in this example, right? Right, so you can hear that sort of pitch now, which comes from the mode of the cavity. And then finally, you can go put these in a big room. Okay, so these are things I've talked about so far, really models of things that already exist out there in the real world. So something like a snare drum, I mean, we know what that is. Like for musicians, like the ones I've worked with, like the thing they're most interested in is going and building their own, right? So musicians are control freaks, right? Like they want to control every aspect of the instruments that they're building. And this is one way for them to do that, right? So you give them a bunch of components and allow them to connect them up. So in this case, it's a bunch of metal plates connected with nonlinear sort of springs, right? And this is an early piece I did with a composer who was also SARC based back in the day. This is Gordon DeLapp, who's now at Maynooth. And this is this is from 2009 actually. And this was pure MATLAB generated sound. So the interesting thing about that piece is that was one instrument actually being played on all different parts of it. So he spent most of the time that he worked on this just building the instrument. And at the very end, he developed a score for it. He just ran it through. So that was one run of a MATLAB code actually. So yeah, thankfully we don't have to work that way anymore. But those were the old days. And then finally, this was just for Jacob, but he didn't show up actually. So I just wanted to say a little bit about springs and show a video here actually of a spring reverberating. So this is a real tough system. Like a lot of respect to Jacob for taking this one on. It's tough, but you can, I mean, the same kinds of things apply that I've been saying for about rooms and about instruments in the case of something like this, where we're looking at a curved piece of metal vibrating in order to give you a particular reverberant characteristic. And you can do this too. So here's a typical kind of spring IR, which you probably recognize if you've ever kicked over an old amp, it juggles and makes that sound. Okay, so the computing side, let's just take a look at the runtime loop actually. Like, what do these codes look like when you implement them? And just suppose we have a linear system, which is very unrealistic, by the way. Like any kind of physical modeling synthesis method will look like some kind of state space form, like an audio rate recursion. So we're running over time steps. And the key line here is the first one here. This is the one that maps your current set of states, right? Which could be anything. They could be the pressures within a room at all the different points within it. They could be the displacements of a string. And it maps them at the last time step to the next one, right? Through a linear operation here, right? So this is just a matrix multiplication. And then you can insert input, and then you can also draw output. And this is the full extent of it. And then the very last thing you do at each pass through the loop is just reset the step and then do the same thing again. That's it. So the key parameter then is, like, how big is this, right? Like, how big is this state? And I'll get to that in a second, but it can range from very small to very, very big. these matrices that define this state space system are in general, like, well, depending on how you design your method, like ideally they're very sparse, right? So, and this comes from the fact that all the mechanics and the dynamics are encoded like into these matrices, particularly A, right? So A is like usually looking at local interactions between points on some grid, meaning that most of the values are 0 in there, which is good for us. Like we want that. Like both in terms of storage, because like this A may be something we may need to store, and also in terms of the flop count, right? So both of these things are like reduced actually when you have a sparse form like this. Now in the nonlinear case, where it gets more interesting, like in the most general case, you don't have this anymore, and what you have is a set of nonlinear algebraic equations to solve at every time step, which is very costly. Like like usually you have to do this with something like an iterative method, like Newton or Raphson, which is like inherently serial, so you can't parallelize iterations through something like Newton or Raphson. And then, so it's immediately going to be slow. So like a lot of effort by like various different groups, Martin's group here, mine, others in Paris actually have been like devoted to trying to find like faster ways to do this. And like eventually, so if you do a lot of work on this, you can get this into such a form that you have a kind of an explicit update, which is stable too, and I'll talk about that in a second. And you can interpret this really as a large kind of nonlinear IIR filtering operation. Okay, now for problem size, this is something you can estimate for like a given audio rate that you want to work at. And the way you would estimate it is by counting the number of, for a linear system at least, the number of modes like within a given band of frequencies. And at something like 44.1, right, the audio rate, like here's what you find, like kind of what you expect. So one-dimensional instruments don't cost very much. So the number of degrees of freedom, so this will be the size of your vector that you're updating, will be on the order of hundreds, you know, maximum. And then things get bigger as you move into 2D. So you start looking at plates, membranes. Then they're larger, and then finally there's this big gulf, right, and you end up in 3D, where the number of degrees of freedom goes like well into the billions, tens of billions, like depending on how big your room is. And just for reference, like if you wanted to develop a plugin or something, and you wanted to limit yourself to 20% CPU, like on a typical like commercial grade CPU, like you can do about this as of a year and a half ago. Like this is about 4,000, 5,000 modes or degrees of freedom. So meaning you can do most kind of like tube-like instruments, stringed instruments, and then plates are also kind of doable. Membranes are harder though, actually, right? So membranes cost more, and rooms are still like years away. Okay, so a big problem in audio simulation is to keep these stable, because we have these big, very low loss nonlinear systems. We want them to run for long simulation durations, or maybe like in perpetuity. Like if you give someone a plugin, like they should be able to turn it on and it should just run like forever, like without blowing up on you. And you see this kind of stability in like many different guises, right? So you can happen over the interior of a problem. So here's an explosive growth happening in a poorly designed method. Here is instability happening at a boundary. So this is a poorly chosen numerical boundary condition. And it gets harder and harder to control this, actually, the more complicated your model is, right? So the more components you have interacting, the more chance there is that this thing will explode on you. So for musical use, like it's really important that stuff like this works. Like when you give this to a musician, they get very frustrated like quickly, actually, if things are breaking on them, they don't understand why. So it's like for us, it's been really important, and like actually for Martin's group too, to make sure that to design stuff that really behaves well all the time. So you always get some kind of sound out. And the way that we have gone about this, the way many groups have done it actually, is to look at notions of energy conservation in order to do this. So we look at the system, we figure out a conservation law. We figure out what is this, like what is the stored energy of this system? What are the mechanisms of loss and power input. And we try to mimic this behavior, or actually really transfer this behavior to a discrete time algorithm. And just as an example of this, like let's take the case of something like a room, where we have, this is not the most complicated geometry ever, but you can see it's non-trivial. So this is kind of an amphitheater shape. And we have kind of complicated like impedance conditions on the walls and stuff. We have viscothermal losses in the interior. And what we're plotting here in the top left here is how much energy is stored in each of these components over time, or how much loss is accumulated through these loss mechanisms. And what we want is for all this to add up to some constant, like down to machine accuracy, down to 15 or 16 places if we can. And that is our kind of guarantee of stability for a system like this as a whole. So it's been really kind of an essential tool for us, for everything we worked on, like is to try to build this in. And if you do it right, what you see is if you look at these variations, like down in the bottom left plot, you should see variations that are like down at the level of the lowest bit, right? So you should see these kind of stripes occurring, like it's quantized. Okay, so for nonlinear systems, this is the difficult part actually for physical modeling. And I just wanted to give you a couple of examples of nonlinear systems just so you can hear the effects. So one is, this is kind of the lighter of the two examples. So this is the case of string vibration at high amplitudes. And I've got here a spectrogram of a string being hit several times, like at increasingly high amplitudes. And you see these kind of effects here, right? You see, first of all, there's a brightening of the timbre, but there's also this pitch glide occurring here too, like it's stronger with each hit. And first I'll just play the case of a linear model, where we don't have this effect. So this is a pure linear model, so each of those sounds is just like a scaled up version of the previous one. There's no other effect there. However, when you have the nonlinearity, there's really a lot going on there. So you have the pitch glide, but then also these real changes in timbre. It's much, much richer, actually. And then this is the really kind of heavy example, the case of plate vibration. So thin metallic structures form the basis for many percussion instruments, so gongs, cymbals, tam-tams, etc. When you hit these things hard, you get really strong nonlinear effects, as you know, right? So if you think about a cymbal crash or a gong strike, a big one. And it's a very different kind of nonlinearity from the kinds that you see in, say, like an electronic circuit, right? Where you might have like harmonic distortion happening. Like it's much more intricate than that. And so if we just look at the way in which a plate moves at low amplitudes, if we were to deform, say, a square plate into its first modal shape at a low amplitude and just let it vibrate, it would just stay there forever. And what you see is that as you increase the amplitude of that deformation, like you start to see bleeding of energy into higher modes, and then finally, really almost like a chaotic regime emerging. And it's kind of easy to see this by looking at a slightly different case where we take a plate and we drive it with, we put a driver on it, we keep driving it with a sinusoid, and we just crank up the amplitude of it slowly over time. So this is the spectrogram of what you get out, like over a 10-second period. And like I'll just explain the spectrogram before I play the sound, but what you see down at low amplitudes is the whole plate just vibrating at the driving frequency, which is linear system behavior. And then you see harmonic distortion. So this is the typical nonlinear effect you see in electronic circuits. But then, like if you keep raising the amplitude, these all start to split, right? They start to bifurcate at about 6.5 seconds. And then there's a chaotic regime here, a turbulent regime, corresponding really to the noise you hear when you hit like something like a cymbal. So I'll just play the sound now so you can hear this. So this is synthetic, by the way, too. Okay, now just a little bit about music now. This is the last part of the talk here. We ran a couple of projects like in the last decade. Feels weird to say that, but from 2012 to 2018. And they were concerned with really all this stuff actually, like everything to do with room acoustics and also effects modeling, musical instrument synthesis, etc. And there was a bunch of people working on algorithm design, so me and a bunch of PhD students, postdocs, where the job was to go from some target system, figure out a mathematical model for it, which is kind of non-trivial because there are a lot of choices, write prototype code, and then be able to produce sound. And then there was a whole team devoted to hardware acceleration. So these were people that worked at the Parallel Computing Center in Edinburgh. And their job was to speed this up as much as possible by porting it to GPU, sometimes like trying to accelerate performance on the CPU, sometimes a hybrid of CPU and GPU for certain types of instruments. And then finally we invited over a bunch of musicians, I think 7 or 8 in the end, to come in and work with us and do pieces. And this was really the most interesting part of the project actually, was to really listen to what they had to say about these instruments. And oftentimes the things we thought were interesting were not the things that they did. And also, like, sometimes they were really got focused on things that we didn't care about at all. So we had to really recalibrate, you know, based on what we learned. Because, you know, in the end, the musicians are they're the bosses, right? Like it's for them. So we did this through a bunch of workshops, and there are a bunch of pieces that are out there on YouTube. You can go listen to the stereo reductions of them. They were all multi-channel, by the way. So minimum 8 channel, maximum 32, I think. So I'll just play a couple of, these are stereo reductions, so it's kind of hard to hear what's going on. Like, these are designed to be kind of immersive, but the first one we did was by Gordon DeLab from Maynooth. And this was that was really brave. Actually, it took 6 months for him to figure this stuff out. And he managed to do a 9-minute, 3-part piece. And this is like he worked mostly with brass, and then also somewhat with a bass drum model we had. And then he also ran a lot of it through big reverberant plates, actually, kind of in a plate reverb type effect. So this is... And then Alberto Torin was one of our PhD students, and he got really, I think, distracted at some point during his studies, and then said, you know, I really don't want to do any math for a while. And I was like, okay, like, why don't you go do some music, you know, with the thing you're working on. So he went and did a little study for gongs. This is all 3D sort of modeling of gongs, actually. So this was, again, multi-channel. And then finally, this is, I don't know if this is the same one I played earlier, but this is a bit of Gadi Sassoon's Multiverse, which was done partly with guitar model and partly with a big modular network. So, yeah, it's the same. Wow. Okay, so all of this stuff is offline. So this is all done on our GPU system, which you could log into and produce sounds on. you don't need to do that anymore. We've released all the code open source, so that's just sitting there now. We've shut down our GPU server, but you now have the code, so you can go and do what you like with it. But at the same time, we got interested in trying to convert what we could from this into real time. So we formed a company, so this is with two postdocs, Craig Webb and Michele Ducheschi, to see what we could do in real time. And the first product we did was something called Derailer. So this is a bunch of vibrating bars. This is like a very kind of stripped down version of that network that I showed earlier, the one that Gordon worked with all the plates. So this is now the real-time version of that. And you know, it's okay actually. Like I think these days I sort of listen to it and it feels a bit like there's not a lot of variety actually, but there's some. So you can do kind of struck sounds. Also accepts bow input as well. And then also you can send in like external signals too. Like so if you want to just send in, like use it as a plugin, you know, and just have some other plugin sending in a waveform or something, you can do that. Hey. And then the next product was something called preparation. So this was kind of inspired by prepared pianos. So we would have pairs of strings where for each pair you can specify a kind of a rattling element. And what you can specify there is how heavy it is and like how stiff these little wings are that it has on it. So it's able to kind of interact with both of the strings. So you hit one, it'll set this sort of rattling thing into motion, which will eventually set the other string into motion too. So there's a, like, you know, roughly, I don't know, 15 or 20 parameters, like per string plus rattle pair that you need to cope with there. And this is about what you can do in real time, or what you could do in 2021. So you could get about 25 of these things running, like at, you know, 10 to 20% CPU. And I'll just, before I play this actually, so these are a couple of just videos of Craig Webb actually playing this thing like in real time. And the first one's very simple. I think it's just altering the, I don't even know actually, this, the stiffness of like, I think that component, like while he's playing, I think. So this is where I think he's got stuff mapped to the mod wheel now, so where he's controlling both force and velocity. Oh, wait. Yeah, so you get these kind of feedbacky tones, sort of reminiscent of like electronic feedback, but now totally mechanical, right? And then the final case is just the case of what happens if you just turn the loss down really low and just hit these things. So there's no, energy's not damping out. So what happens is the thing just will keep rolling like forever. So you can like let it roll for half an hour. I can come back and see, and then because the nonlinearities are so strong, like even very slight variations in how you initialize it will lead it to kind of drift off somewhere else. So you get really interesting stuff actually, and this is yeah, this is one of those. This one, yeah. So this is with a bit of loss, right? But you can actually turn off the loss completely, and then it just will remain like vibrating like forever. So in terms of spatialization, this is something we haven't really figured out yet. So at the moment, everything's stereo. There's a quad version, I think, which I think you have to ask Craig for if you want it. But like that's always an open question. Like when you have a lot of these things, like what do you do with all the sounds, or how could you map this to make a whole like set of loudspeakers or something? We don't really know. Anyway, so oh yeah, and it's getting late, right? Are we overtime now? I can safely skip.
4:05, we're doing, you know, I don't know if anyone has to leave.
All right, this is my last slide. So just to say, like we're sort of continuing with like trying to turn everything we can into real time. So the next step was to try to look at something like 2D, something like a gong. And so we managed to sort of do this in 2023. And there's a kind of prototype plugin. This one's not for sale, but you can ask Craig for it and he'll send it to you. But it can just do like one gong, basically, you know? So it's not like super exciting to play with. Like there's not really enough variety for it to be like an instrument that you could sell. Or maybe there is, I don't know. Like, but when you're striking it, like it's cool, but you can only just do this sort of one sound, like. Now, where it is interesting though, maybe, is like where you start sending in like sounds from outside, actually, off-board sounds, like something like a sine wave going in. So this is just pure sine wave excitation. And again, like kind of like that case of the plate, you start to get in some weird, sort of very chaotic sort of regimes here. So that's actually really fun to play with. Like we had a demo of this running like during DAFX, and like you could sit there and sort of change the frequency that you were driving it with, and the amplitude and stuff, and you could sort of drive the plate off into different regimes and stuff. So it was very fun, actually, like more fun than hitting it, you know. And then this is the last slide here, just to say, there's like you can really kind of do stuff like in real time now, like a relatively large thing. So gongs, like large sets of strings and stuff. Some things are just expensive though, like inherently. So like rooms, like they're still offline, and they probably will be for a while. But, you know, like not dirt cheap. Like, so compared to like a procedural audio method, these are still cost a lot more than that to run. We spend a lot of time like working on very specialized designs, like to make sure that these things behave well numerically. So that's almost the main job in some ways, is to make sure that these things behave well. Like before we can even get to the stage that they can be used musically, like you need to just keep testing them and make sure they behave well. And then finally, like just, you know, for people who are, I don't know if there are any machine learning people here. Or anyone? No? I kind of thought there might be, actually, so I put this in there for them. But yeah, like, there are some interesting kind of constraints that come out of thinking about things physically. Like, say these like numbers, like these estimates of state size or something like that. Like, that's a good thing to know, like if you're going to design the neural network. Because one thing like I'm noticing is that these neural networks can become very large. Like the number of, you know, the state sizes in them can be much, much bigger than what you would need for a physical model. So like perhaps like you can use what you know about these estimates like to try to guide your choices of like state sizes for a neural network or something like that. So I don't know though, that's still very kind of easy for me still. But that's it actually. So,
All right.
thanks everybody.